Hi, I'm Chris Fulton, and I'll be presenting some of my research and data surrounding static thresholds versus their statistically derived counterparts with regards to anomaly detection. So what's the problem that we're actually trying to solve here? Essentially, threat detection engineers will create a lot of detections based on very high volume log sources. So something like AWS CloudTrail or raw network logs, where it's very easy for these log sources to be in the hundreds of thousands per hour. And within these environments and these logs, threats like denial of service or data exfiltration exist. And the traditional method to detecting these is by using essentially log counts. So, for example, if there are more than 1,000 logs in 15 minutes, generate an alert. And the issue with these sort of static thresholds where they don't change is that they're set once by the threat detection engineer, and then they don't adapt to the data changing, the business changing, and the log source potentially growing. And the result of that is that false positives will be generated. And that, in response, creates a lot of alert fatigue for whoever's triaging them. So either the threat detection engineer will end up having to continuously retune these detections with a new threshold that relates closer to the real data that they're working with at that point, or they just sort of have to live with the false positives, or worst case scenario, they set threshold too high and miss true positives. The other issue here is that SIMs functionally are just, or traditionally are querying machines, and they don't have the computational sort of infrastructure to do really, really heavyweight statistical analysis, to deploy a statistical engine model, things like that. So in the research that I read through that sort of relates to this, there are a lot of really well-known and very strong detection models out there that use Bayesian clusters, things of that nature, where it's really, really high-end. People with statisticians essentially will create these detections and create large models and engines that are very good at detecting anomalies. But the issue is that SOCs oftentimes will just have a sim that can query data, and that's functionally all it is. It doesn't have the backbone of being able to run a dedicated cluster for statistical analysis. That's oftentimes what you would see with a web application firewall, where you hire a company to determine if there's an attack in your environment. The other side of this is that if you did employ something too complex, like a very, very complex statistical model to detect anomalies in your environment, you can't make it so difficult to understand that an analyst wouldn't be able to interpret what it means. Because when they get a detection and or a threat detection engineer has to tune it, a real human has to go in and understand what's going on. So there's some significance there to making it almost simple, definitely lightweight, where it can run in your environment and also be understood by people in your environment. The last part sort of highlights that alert fatigue is a very real thing, and it is well documented, well studied within SOC environments, and sort of highlights how critical this problem is, especially with regards to high volume log sources. So the hypothesis that I'm basing this off of is that threshold-based detections using statistically derived thresholds will essentially perform as well or have comparable efficacy to static thresholds while reducing the need for tuning as often or at all, and will have less false positives because it's continually doing that statistics and it's not based on one point in time of data. So here's how I implemented a test for this. I created a mock data set based on a 90-day period And I set some parameters where it would mimic sort of a real business environment. So it has two bell curves around 10 a.m. and 2 p.m., sort of symbolizing the peaks of productivity in the day. There's sort of a dip for lunch and at the beginning and the end of the day. And before 9 a.m. and after 5 p.m., there are drop offs because people aren't logged into their workstations. There's not as many customers logging into the portal, things of that nature. On the weekend, it drops by 40%. This symbolizes that the systems are still running, still operational, still generating logs, but you might not have active humans on keyboard, active people logging in, things like that. And the most critical one, in my opinion, is that over this 90-day period of mimicked data, the log volume grows by 30%. So at the end of this 90 days, it'll be 30% higher than it was on January 1st, where it starts. And the thresholds that I created to test and compare to each other, one is a static threshold. It's using the first 7 days of data, taking the log normalized average of them, and then setting a threshold that is 2 standard deviations higher. And 2 standard deviations just typically what people consider statistically significant. So it's a fair baseline, I think, to set for anomaly detection. The rolling threshold, and this is sort of the crux of the test here, is continually computed based on the previous 24 hours of log normalized data. So it evolves every day. It's different. Technically every 15 minutes that this runs, it is a different threshold. And it's still computed as the mean plus 2 standard deviations, but it will react to data as it sees within that 24 hours. So here's some sample KQL that you could use. Custo query language. This is what Microsoft Sentinel uses, which is one of the sort of forefront SIM tools right now. I'm using this in my environment. Obviously, I've sort of sanitized it for this demonstration here, but this is essentially an example of how simple and lightweight this detection is and how you can actually use it within a query language itself. You don't need a very, very heavy computational engine at the back of it, although obviously KQL is very strong, but it's still at the end of the day a query language. It's setting variables, it's doing a little bit of math, but it's not so overly complex that an analyst wouldn't be able to understand what's going on. So here's how I went about testing the two thresholds. I created 3 attacks essentially to put into the simulated environment. Since these thresholds don't use like signature matching or anything very complex, it's purely looking at the volume of logs. These are just injected spikes of data over a period of time. So the first one is sort of a denial of service style where it's a really big spike in data very quickly. That's on day 30, and it's 6 times the normal log volume. On day 55, there's a sort of lower, still higher than normal log volume. It's 2.8 times the normal log volume, but that's over 6 hours. So it's definitely a lot more sustained than the denial of service one. And then I put another sort of sustained one closer to the end of the experiment on day 80, where it's 4 times the normal log volume over 2 hours, just sort of has some variance there. But I put it at the end because that should be able to show some of the threshold drift that we'll see with a static threshold and the improvement that a statistically derived threshold will have over a static one. As these are essentially very simple logs, they don't have real data, very simple to create with Python and a couple packages to sort of visualize and analyze that data. So the results of that data, we can see the initial rolling threshold is this green line. The static threshold, which ended up being 7.76, this is log normalized events here, is the red line here. And you can see the denial of service attack is this faint red line. The exfiltration attack is this faint orange line. And then the further in the cycle attack is this purple line here. And these lines that you can see on the chart is the volume of logs. So you can see on the denial of service day, it goes up very high. And this is all obviously all log normalized, so it's easier to visualize on a graph. But we can see on this side the alerts that it generates. So there are a couple false positives here within the rolling statistical average. That's the green lines. Looks like there are a couple that are outside the static or the traditional bound of the attacks here. But the more important thing is that on the static threshold, we can see that since the volume of logs is increasing over this 90-day period, we start to get a lot of false positives that are outside of the attack periods here, where near this drift attack, these these alerts being generated would probably mask a real attack because they're so common. An analyst might, get alert fatigue. They might not look as hard into these alerts because they're so common, and an attack within this period might get missed. That's sort of a pretty critical point here. So here's the findings of the experiment. Over the 90-day period, there were 34 alerts for the static threshold, with 28 of those being false positive, which is alerts outside of the attack window. And for the statistical rolling average, there were 23 alerts, with 17 of those being outside of the attack window. So there were definitely a decrease in false positives, which is good. That's what we want. And very, very closely correlates to the 30% increase in log volume, where both of these detected adequately the attacks being performed. But if that environment hadn't increased by 30%, the static threshold would probably be comparable to the rolling threshold, which, simulates the fact that maybe rolling threshold isn't useful in every possible scenario here. If you're seeing a really standardized environment, maybe you don't need statistical thresholds in there. Static thresholds might work. One weakness that was revealed to me through this process was that the rolling thresholds started to get less sensitive to an attack when the period started getting longer. So if an attack slowly increased in volume and gave the statistical engine or the statistical threshold time to catch up, where it just slowly raised that average over, say, 24 hours, an attacker could technically go through with their attack without any detection happening. And that's sort of definitely a weakness with it, and sort of exposes maybe a hybrid solution might be best in this case. Um, Definitely, it's an interesting result, essentially. So in future, I think uh, investigating that hybrid approach, maybe run a static threshold in parallel with a adaptive statistical threshold, that would probably be a very robust solution. Additionally, entity-based thresholds, this is just looking per IP. Are they hitting that statistical threshold? Are they hitting a static threshold? You could do entity-based thresholds statically as well. Testing this in a real environment would definitely be really useful data as well. And then being able to compare a couple other methods. Obviously, this is just one. This is essentially a rolling window. There are a lot of statistical methods out there to determine what an anomaly is, and I think that would be very useful data to see. And if they could be implemented with a query language, that would probably that'd probably be really useful to sort of compare the two against each other. And here I have my references. Thank you for listening.